Welcome to this detailed exploration of the NPN Bipolar Junction Transistor, or BJT, a fundamental building block of modern electronics. What you're seeing is a complete visual guide, showing its physical structure, its circuit symbol, and the essential mathematical relationship governing its behavior. Let's begin on the left with the physical model. A transistor is essentially a semiconductor sandwich. In this case, it's an NPN type, which means it consists of a thin layer of p-type semiconductor material, called the base, placed between two layers of n-type semiconductor material, named the emitter and the collector. The n-type material has an abundance of free electrons, which are negative charge carriers, while the p-type material has an abundance of holes, which can be thought of as positive charge carriers. The emitter's job, as its name suggests, is to emit these electrons into the transistor. To do this, it is heavily doped with impurities. The collector's role is to collect the vast majority of these electrons, and it is the largest of the three sections to help dissipate the heat generated. The base is the crucial control element. It's very thin and lightly doped. For the transistor to work in its most common mode, known as the active region, we must apply specific voltages, a process called biasing. As shown in the diagram, the emitter-base junction is forward biased by the voltage source V_B. This means we apply a positive voltage to the p-type base relative to the n-type emitter, which reduces the natural barrier between them and allows electrons to be easily injected from the emitter into the base. This flow of charge into the base terminal creates the small base current, I_B. Simultaneously, the collector-base junction is reverse biased by the voltage source V_CB. This means a much larger positive voltage is applied to the n-type collector relative to the p-type base, creating a strong electric field across this junction. Because the base is extremely thin, most of the electrons that are injected from the emitter do not have a chance to combine with holes in the base. Instead, they are immediately swept, or attracted, across the base and into the collector by this strong reverse bias field. This massive flow of electrons constitutes the much larger collector current, I_C. This is the essence of transistor action. A tiny base current, I_B, enables and controls a much larger collector current, I_C. Now, let's move to the right side to see how we represent this complex device in a schematic. This is the standard circuit symbol for an NPN transistor, with terminals labeled B for base, C for collector, and E for emitter. The most critical feature to note is the arrow on the emitter leg. For an NPN transistor, this arrow always points away from the base, indicating the direction of conventional current flow. A helpful mnemonic is NPN, not pointing in. The diagram also shows the currents I_B and I_C flowing into the transistor, and the total current, I_E, flowing out of the emitter. Finally, encapsulated in the dashed box, we see the fundamental equation that ties everything together, I_E equals I_B plus I_C. This is based on Kirchhoff's current law, which states that the total current entering a point must equal the total current leaving it. In this case, the emitter current is the sum of the small base current and the large collector current. This simple equation is the cornerstone of all BJT circuit analysis, perfectly summarizing how the currents within the device are related, and reinforcing the concept that a small input at the base can control a large output at the collector, making the transistor a powerful amplifier or a fast-acting electronic switch.